Hi guys, Assalamualaikum. Welcome back to Learn Physics in 15 minutes. Are you guys excited? Because today we are going to learn new topic, which is Chapter 6, Nuclear Physics, with the first subtopic, Radioactive Decay. As usual, I will expose to you the learning standard. It will help you guys to get prepared with the context of the topic, since the topic is quite tough, but not difficult, okay? So, at the end of the video, you guys will be able to explain with example decay equations of alpha decay, beta decay, and also gamma decay. Oops! Before that, do you guys still remember about radioactivity that you learned in Form 3? Never mind. Let's recall about that together. As the introduction of today's lesson, let's start with what is radioactivity? It refers to the particles which are emitted from nuclei as a result of nuclear instability. This is because the nuclei experiences the intense conflict between the two strongest forces in nature. It should not be surprising that there are many nuclear isotopes which are unstable and emit some kind of radiation. Hence, the most common types of radiation are called alpha particle, beta particle, and gamma rays. When these particles pass through the air and produce positive and negative ion, it is also known as ionizing radiation. Let's see what are the characteristics of each radiation. We start with alpha radiation. Alpha radiation consists of two protons and two neutrons bound together into a particle identical to a helium-4 nucleus. It is positively charged particle and deflects in electric and also magnetic fields. It has the least penetration power and can be stopped using a sheet of paper. But it is more dangerous if they can enter our body, as they have the highest ionizing power. Next, beta particle or beta radiation. It is high energy, high speed of electron. It is emitted by the nucleus. Therefore, it is negatively charged. So, it also can be deflected by an electric and magnetic field. It has greater penetration than alpha particle, and it can travel through the skin, but can be stopped by using sheet such as aluminium. Its ionizing power is less than alpha, but still it is harmful and can damage our body. Last but not least, gamma ray. Gamma ray is a high-frequency electromagnetic rays. It is emitted when the nucleus comes back to ground state. It does not have mass and charge. Therefore, it can't be deflected by electric and also magnetic fields. It is highly energetic and can penetrate our skin easily. It can even travel through slabs of aluminium, lead, and even thick concrete. Its ionizing power is the least among them, but it has sufficient energy to damage our DNA. So now, we can continue our lesson with what is radioactive decay and how to write its equation for each alpha decay, beta decay, and also gamma decay. Radioactive decay. It is a random and spontaneous process where an unstable nucleus emits radioactive radiation until it becomes more stable. It is a property of several naturally occurring elements as well as of artificially produced isotopes of elements. Here are several examples of isotopes that have unstable nuclei and decay spontaneously by radiation. Carbon-14, Radon-222, and Uranium-238. The product of radioactive decay is called the daughter of the parent isotope, which may itself be unstable, in which case it will decay too. This process will continue until a stable nuclide has been formed. These emissions of the most common forms of spontaneous radioactive decay are the alpha decay, the beta decay, and also the gamma decay, which we will go through one by one after this. First is alpha decay. During alpha decay, an unstable nucleus releases an alpha particle to become a more stable nucleus of a new element. This figure shows the process of alpha decay. Therefore, we can write that the general equation for alpha decay is as shown. But the question is, why the equation consists of helium symbol? This is because the alpha particle is a helium nucleus which consists of 2 protons and 2 neutrons. Here, the parent nucleus has a nucleon number A and a proton number Z. So, after the decay process, the daughter has nucleon number A minus 4 and the proton number Z minus 2. Since the alpha particle has been separated from the daughter nucleus. Hence, we can say that the equation is balanced, which the value of the left side is equal with the right side. Here is an example of alpha decay. Polonium-210 is a parent element with the nucleon number 210 and the proton number 84 will produce lead as its daughter element plus with the alpha particle. So, the value of lead's nucleon number is 206 and its proton number is 82 as the nucleon number need to be subtracted by 4 and the proton number is minus by 2. Next, we move on with beta decay. As we know, beta particles is a fast-moving electron. During beta decay, a neutron in an unstable nucleus decomposes into 1 proton and 1 electron. The resulting proton remains in the nucleus, while the electron emits with high kinetic energy as beta particle. The figure shows the process of beta decay. So, the general equation for beta decay is as follows. The beta decay result shows that the proton number of daughter nucleus is 1 more than its parent, but the nucleon number, which is the total number of neutrons and protons is the same. Therefore, we can see that the equation is balanced, same as alpha decay equation. For example, carbon-14 with nucleon number 14 and the proton number 6 decays to nitrogen-14 with emission of beta particle. The nitrogen has one extra proton number, which is 7, but the nucleon number does not change. In comparison with other forms of radioactivity, such as gamma decay that we will learn next, or alpha decay that we had learned earlier, beta decay is a relatively slow process. A third type of radioactive decay is gamma decay. During gamma decay, an unstable nucleus releases its excess energy to become more stable, as shown. In most practical laboratory sources, the excited nucleostates are created in decay of parent radionuclide. Therefore, a gamma decay typically accompanies other forms of decay such as alpha or beta decay. Since gamma rays are high-frequency electromagnetic waves and have no mass or charge, so we can simplify its general equation as shown. After gamma decay, there is no changes in proton number and also nucleon number for parent nucleus and also daughter nucleus. It is just the nucleus become less energetic after the decay. For example, in the decay of radioactive technetium-99, a gamma ray is emitted. We can see that the identity of parent material does not change, as no particles are physically emitted. A superscript M here is known as isomers. Isomers are nuclide with equal proton number and equal nucleon number, but different energy states. Sometimes, the radioactive decay of a sample can result in the release of multiple forms of radioactivity. It means some nuclei can emit more than one radiation. For example, in the radioactive decay of uranium-234, both alpha and gamma radiations are emitted. Its decay equation is as shown, but the decay equation actually can be written in a simpler way like this. So, in order to ensure that you guys focus and understand today's lesson and also able to achieve today's learning standard, here I have prepared an exercise for you to try on. The situation is strontium-90 decays to yttrium-90 by emitting a radioactive particle. The symbol of strontium-90 and yttrium-90 are given. So the question are, write the equation for this decay. Second, explain your reason for answer A. If you guys are able to answer this exercise, great job, because you have passed the learning standard. But if you are unable to do so, don't worry, you just need to work harder. Don't give up easily, okay? See you next time. Bye-bye.